our group that's doing about the Fourier Transform. But what is the Fourier Transform? Well, it's called the Fourier Transform because it was invented by Joseph Fourier, a guy who came up with it in 1822. It's a transform because it transforms a signal into another type of signal. In this case, it takes a signal from the time domain and it transforms it into the frequency domain. We should hopefully be explaining what it is and how you can use it.
So signals in nature, science, engineering and our daily lives are composed of waves. The wind makes water waves, light and sound travelling waves, and even movement of large crowds and traffic, and of course Mexican waves. Sound is created by changes in air pressure. The faster a sound wave oscillates, that is, the greater its frequency, the higher the sound's pitch. The taller the wave is, or the greater the amplitude, the louder the sound. This means that we can describe a sound by giving its frequency and amplitude over time. The problem is, sound signals in everyday life aren't simple waves like sine waves, which can be described easily as the frequency and amplitude remain constant. Natural sound waves have different frequencies and amplitudes at different time points, so storing all the numbers to describe them would be difficult and take up a lot of memory space. Luckily, complicated waves are always just combinations of simple repeating waves, sinusoids, and if we know the data on these, we can reconstruct the original wave. What the Fourier transform does is find the frequencies of these component waves.
So, what is the actual Fourier transform? Well, here it is. It looks kind of scary, but actually, it's quite simple. You see, this part here, this is the integral symbol. I'm sure by now you're all experts on integration. This is telling you to integrate the entire equation between the bounds of negative infinity and infinity. That might sound impossible, which is because it is. But luckily, because we're all finite beings, we only need to do it in a finite amount of time. For example, if we're taking a sound signal, you only need to do it between the beginning and the end of the recording. This bit over here is the actual sound signal. This is the bit you put into the equation. The df over here, this is the end of the integration. Imagine it as the closing bracket for the integration and the symbol being the opening bracket. Which leaves us with this. But what does the E mean? Well, the E is actually Euler's number, which is equal to 2.718281828459, or near enough. And we'll be learning more about this later.
So I will talk about imaginary numbers and complex numbers, which are a pretty big part of Fourier transform. So when we square 1, we get 1. When we square minus 1, we also get 1. So what can we square to get a negative number? Well, if we square root minus 1 and then square it, we get minus 1. We also call this number I, the imaginary number. In complex numbers, they're usually written as A plus BI, A being the real part and B being the imaginary part. We can also draw a graph with the x-axis being the real dimension and the y-axis being the imaginary dimension. We also have R, which is also called the modulus, which is the distance from the origin. And we can also work out Z by doing some trigonometry and Pythagoras.
So, as Marley said earlier, the E in this equation is Euler's number. With this, he explains that e to the I pi plus 1 is 0, which we can derive to find e to the ix equals cosine of x plus I sine x, where x is a real number and I is an imaginary number. We can draw this on the real and imaginary plane, and it creates a circle. And with this, we can find any number on this graph, which is a complex number. And this can be noted down as E.
Before we go on to applications, we would like to show you a program that we've used in MATLAB, which is a language specifically for maths computations. It has a fast Fourier transform function. If we record a sound, it will return a graph showing the frequencies within the sound. Using the Fourier transform, we can discover the strongest frequency of sound in, for example, somebody's voice. So could we have a volunteer?
So. When it says go, can you please talk into the microphone or?
I love Fourier Transform.
Wait. Go.
I love Fourier Transform and MATLAB.
Thank you very much. Round of applause for our volunteer. As we see here, we got two graphs. Top graph is sound signal over time, which is kind of a visual representation of the sound recording. The bottom graph shows frequency and shows the strongest frequencies of sound in the voice. There's different colours on the bottom because it's the imaginary part as well as the real part, so the kind of different colours to differentiate which one.
Okay, so it's maybe well and good. I mean, there's a lot of equations in there, but what is it actually used for is what I'm going to explain to you. So, noise cancelling headphones are one sort of technique that use this transform. So the way in which they do it is they take in the waves, so as we've just done, they're taking the amplitude and the frequency, but then they sort of take in the waves and they want to expel them again. But this time we want the opposite frequency and the opposite amplitudes. So as you can see on the left diagram up there, we've got two waves that add together to then create a plane wave, which will have no noise. So then, as these are added together, the person using the headphones then doesn't experience the noise from the external source. Another sort of technique that uses this is voice recognition. So anything with Siri, Google, Cortana, Shazam, anything like that. It takes in the waves again, as we've demonstrated before, and then it sort of compares it to preset data, and then it can sort of produce a response from your command. So yeah, if you say hi Cortana, it might say hi back to you, something like that. Other uses, sort of seismology, that's to do with earthquakes and waves. Also MP3s, which the frequencies can be reduced, so the file size is also reduced. So thank you very much for listening, and we will be happy to answer questions at the end.
We hope you integrate, no pun intended, the Fourier Transform into your everyday lives. And maybe even use it for some interesting applications, like cutting off the low frequencies of your voice to make you sound like a chipmunk. Thank you to Katie and our instructor, Marcus.